Hello, it's a good day. The test was delayed.
Productive day, productive day.
Much
Question,
love.
what would this graph look like?
He's disgusting.
Wait, who is he really? Well, he's a quadratic over a linear, but who is he really?
With a hole.
A line with a hole. So which one's easier to think about, this one or the line with the hole?
The line with the
The line with the hole, because how do you graph now? I know, it's a t instead of an x, but isn't this in the form of mx plus b, but it's mt plus b? Doesn't matter. So what do I do with this line?
You put it on
I start graphing any line by graphing his
Y and
y-intercept. And where does the y-intercept occur?
-1. But then
Negative
the
1. Wait, that's the y though, not the x. And then what's his slope?
1.
Up 1 over 1. Then that's over 1. Up 1 over 1, etc. How do I go back?
Down.
Back 1. Pretend that's a 1. Down 1. Wait. Back 1, down 1. Do I put a point?
No.
Why do I put a hole?
Because there's a hole there.
There's a hole where? At t equals -1. And how do I know exactly where a hole occurs? Because I can take the factored out form and I can be super specific and say there's a hole at x is -1. What would the y be? Plug it in there. No, that doesn't work. Plug it in here, and what's the y? By factoring out the hole, I can see where the hole is. Because I can see the line, I can graph the line, and I can even go back and say, hey, there's a hole. Where? At the -1. Okay. The -1 point, I mean. And then approximately we have our line. Sound good?
In order to do what, you plug in the -2 and the -1 on top.
Down here.
Yeah.
Hold on.
Wait.
Hold
Okay.
on, hold on. So then, that's how holes work, right? Vertical asymptotes, so that's what we were talking about yesterday at the very, very end, right before the bell rings. So vertical asymptote is the other one. What kind of discontinuity is he?
Non-removable.
Why can't he be removed? What? You can cancel everything out. Yay!
Kill the seal.
Massacre. This is horrible.
Because you can't
Poor kittens are all dead.
there anything.
You can only simplify when their factors match. Do they? There's nothing I can cancel out. There's nothing I can remove. So hence it's called a non-removable discontinuity because the denominator cannot be factored out. My domain still says x can't be -2, that's true. And if I think this is what you were asking about, Luca. If I tried to plug in -2, I ended up, and I went really fast yesterday, but I don't end up with 0 over 0. I end up with 7 plus 2 times -2 all over 2 plus -2. The bottom is 0, but what's different?
You don't have 0 on the top.
0 is not in the top.
So that's why it's non-removable.
Well, this shows that it's non-removable. This is a shortcut trick to see that it's non-removable. Since you can't reduce any factors, that's why it's not removable. Does that make sense? This is actually called infinite form, and it always points to a vertical asymptote in question. How do I graph a vertical asymptote? At -2. I go here, and I go there, and then what? Yep. Now what's going on over there? Do you know? So we're stuck, we just can't know anything else about this graph besides it has a little dotted line right there? Oh, we can know more. Let's go explore and we'll come back to this, huh? Leave your graph blank except for a vertical asymptote at -2 and we'll come back. You're not putting your graphs. Shame. Got your graphing calculator. Yes, of course you can figure out things from your graphing calculator, but we're going to use him to help us build up to how to figure out what's going on with a graph with only math. But we're going to start with our graphing calculator. So, how to check the behavior around vertical asymptotes. How to know what the function is actually doing. A hole isn't bad. as long as his function isn't bad when we factor and reduce. But a vertical asymptote is way harder because nothing cancels, so we don't know what the graph looks like. So how do we deal with that? Well, the way we deal with it is we explore, figure out the behavior that's going on around the vertical asymptote. And how do we figure out the behavior? We see the vertical asymptote as breaking the graph, and so then we have to come from below the vertical asymptote and ask, what's the function doing? And above the vertical asymptote and ask what the function is doing. We have to come from below and above and see what's going on. But since the discontinuity is, what do I mean by VA? Vertical asymptote. Since I do have a vertical asymptote, f of x only has two choices as to what he can be doing. Wait, what are the f of x's standing for again? What kind of values?
Y values.
Y values. The heights. The heights have one of two options as to what they can approach. And to help you out with that, let's think really quickly about all the different possible types or ways of coming towards a vertical asymptote. We could either come at it now. You could come at it like high or low, etc. But either as you come in close, the y's are going infinitely up together. The y's are going infinitely down together. Or, have you guys ever seen anything else happen?
It goes down and
They go in opposite directions. One goes up, the other goes down, or one goes up while the other one goes down, either way. That looks like it hits, let's just say it's getting really close really fast, but either way. Look at all these different ways of a function to come in towards a vertical asymptote and get infinitesimally closer to it without hitting. And what would you guys answer as the two different options for where the y's can be going? Either up or down. Now how do we say that in the snazzy way? Remember, thinking about our little approaching arrow. Either infinity or negative. Right? Kind of thinking back to end behavior of graphs, if the degree was even and the leading coefficient is positive, it's going up to the right and up to the left. And we use that snazzy arrow to infinity for f of x. That's what I'm leading up to. All right. We'll get back to our other example in just a second, but for right now, we have another one. What's his domain?
Oh, God.
Good. X cannot equal -1. What is occurring at -1? Whole or vertical asymptote? Why? Okay, one way is to plug it in and say, what is happening at -1? And I can say the top is -3 and the bottom is -3/0. And that's a hint because it's like, hey, those aren't the same, retro, we're not going to be able to factor. That's a hint. But you can also look and say, can I cancel out the denominator? Can I factor it out? Can I reduce it? No. He's stuck. Oh, well, since he's stuck, the discontinuity is stuck. So I can say there's a vertical asymptote at x equals -1. Whether you like the plug it in, it's a number over 0 clue, or whether you like the look at it, it can't factor and reduce, either one points to a vertical asymptote. Make sense? Got a few head nods. Now, if you were allowed to use your table and or your graph, if you were allowed to use your calculator, how would you explore what's going on around this vertical asymptote? You'd graph them, right? So throw them in your y1. Throw them in your y1. Just a few, you might be like, we had a parent function like this once upon a time. It was just 1/x. I think this one's been shifted to the left one. There's a negative, it's been reflected. Maybe some of you could use that parent function to your benefit. But not all rational functions fit that parent function, so I can't just stop there. Now if you guys notice, I'm starting technically with the table. Some of you might be cheating and looking at the graph, and that's okay. We'll get back to the graph in just 1 second. But what we can do right away, without really stressing much at all, is we could say, hey, I know the graph, no matter what, is gonna have a vertical asymptote at -1, right? We know that much. If you were to, you guys see how I'm in my table set up over here? If you do second window, you can have it start at 0, I don't care. Go down to ask for the independent. Remember, that's the one where we can type in stuff. Go to ask for the independent. Your function is in your y1, otherwise you're in trouble. And then go to your table. Question. What am I showing in the table as we plug in -0.5, -0.9, -0.99, -0.999? Where are we coming, or how are we coming to -1? From above it on the number line or from below it? Look at your numbers. -0.5, -0.9, think about your number line, just go horizontal. Where would -1/2, -0.9, -0.99, where would that be? Above or below? To the right or to the left?
To the right.
To the right, because where's -1/2? Well, pretend that was actually somewhat even, like my board was actually oriented, but oops. There's -1/2. Where's -0.9? Zooming in, right? -0.99, -0.99, -0.99. What are we doing? We're approaching, getting closer, we're approaching -1, which is exactly what we wrote down. We have to approach the vertical asymptote. And as we're approaching, and even -1, guys, your calculator has to round eventually, but that's just -0.999, has to round eventually. But it's plugging this in. What's going on with the y? So from above, -1. From above, or you can say from the right, either way, from above, I say above because the numbers are higher on the number line. Or from the right of -1. What are my y values doing? Can you tell? Don't say smaller. I kind of like what you're seeing, but don't say smaller. That's a better way of saying it. Because they're not getting smaller in number. They're getting lower. Where are they approaching? -infinity. Why? It's just getting more negative and more negative and more negative and more negative, etc. So I could say, roughly, and this is just going to be an approximate, I'm not finding intercepts or anything, I can make it better with intercepts. I know somehow my graph is going down from above. Check it. See how these points are going to -infinity? At -1/2, I would need to go -6. At -0.9, I need to go -30, then -300, then -3,000, then -30,000. It's going down, right? What's going on as you look at the table from below -1? And if you like it better, you can say from the left of -1. I'm saying from below because its number's lower. Now, do you see what numbers I'm plugging in to check it? Where's -2? Over there somewhere. Where's -1.1? I'm zooming in, right? -1.01, -1.001, negative, guess what? That's not -1 either, that's -1.0001. Had to round for the table. What's going on to your y's? They're getting higher. So where are the y's approaching? Positive infinity. So what's my function doing as it comes in? It's going up, right? Now, if anybody did look at the graph, does that roughly look like my function? From the right, is it going down, and from the left, is it going up? Yeah. Now, hold on, we cheated just a little bit and we used the table. In the next page, if you guys have noticed, I say, don't use a graphing calculator at all. How are we supposed to figure this out without a graph and without a table? What on earth? Pause. What lets you know? What lets you know? Come on. What lets you know to pick -infinity? The vertical asymptote told you it was one of them. But what lets you know -infinity from above? we even really care about the numbers 30, 300, and 3,000? I guess kind of. But how do we choose between? All we need to know is the sign. So if we don't actually have to know the numbers, if we only have to know the sign, maybe there's a way of doing the math, but not all the way, to where we can tell the sign to keep. Because if it's a vertical asymptote, I know it's either coming from above going that way or going that way, and all I need to do is figure out, okay, what sign do I use? So what if I was to show it this way? Ready? Well, all we need to do is think about the sign. We use the same from, now we know what the answers are. I'm going to say from above and from below. If you like it better, that's my eraser. We can say from the right of -1. It's from above or from the right. It's coming from this direction. Then we're going to do another one from below. No table, no graphing calculator. From below is going to be from the left. All we need to know is the sign, because we know the answer for a vertical asymptote. Which we can tell just from using the math that we did before, and we did not have a graphing calculator for that part. We know it's a vertical asymptote. From above -1, bless you. Here's the statement we're going to fill in. As x approaches -1. Now guys, do you see how many words we had to write for that? If there's this shortcut notation, it would be nice to not have to write all that, right? So here's the shortcut notation. From above, from the right, from -1, a little bit, here's the notation, a little bit more than. We put a little plus in an exponent. Doesn't mean an exponent, doesn't mean squared or cubed or anything else. We put a little plus in the exponent, we're saying from above -1. Numbers a little bit higher than above, to the right. You guys are used to the as x approaches from our end behavior, but then we were saying as x approaches infinity, x was going to the right, but now it's coming from the right towards a number. So that's what's different. But we're still trying to answer the question, what is f of x approaching? And then what do you guys think I'm going to put for the notation of the from the left or from below? Yeah, put a little minus in the exponent. Doesn't mean negative, it doesn't mean, the -1 is there, there's a negative in front, but that doesn't mean negative, it means from below, from a little bit lower than -1. It's a little bit weird because x has to come in towards a number from two sides. So to show those two sides, we put a little plus in the exponent and a little minus in the exponent, okay? But still, we need to figure out what sign. We know if it's a vertical asymptote, it's infinity or it's negative infinity. How do we do this without our calculator? We pick a representative value. We pick a representative value to plug in. So we have our -3 over somebody plus 1. -3 over somebody plus 1. Now I could be super snazzy and super technical, and I could put -1 with a little plus and put that in there, and maybe someday we'll get there when we talk about limits in chapter 12, which is the beginning of calculus. But for right now, can you guys tell me just one of those numbers that was pretty stinking close to -1, but was still on the right or still above? Just one of those from the table. Negative point what? Sure. -0.5. If you want to be super snazzy, -0.9. Or -0.99. What was a number that was from the left? Here's -1 on the number line. What's something over here? 0.5 is this way though. 1.5. We could do that. Is that okay? That'd be safer. probably I'll show other representative ones in the future, like negative 0.9 and negative 1.01, like really close, but just stop. We don't care about the number itself. We know the answers are some sort of infinity. What we care about is what sign is coming in. So check it, kiddos. Just the sign. Isn't the top gonna stay negative? What's the bottom gonna be if I do negative 0.5 plus 1, negative 0.9 plus 1, negative 0.99 plus 1, negative 0.75 plus 1? What are the signs of all of those?
Positive.
Positive, the one wins. But what sign wins overall? Ooh, yeah, and I didn't need a calculator. And I didn't even need to know the number, the answer. All I needed to know was what sign. Now check this one. What sign stays on top with the negative 3? The negative. What's going to win down here? Negative 1.5 plus 1, negative 1.1 plus 1, negative 1.01 plus 1. The negatives will win. But who wins overall? Dun, 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 dun. As I come from below and as I come from above, there are the answers, which I didn't need a graph, I didn't need a table, I didn't need my calculator. Kind of make sense? So let's go back to the one that we had that we're like, what's going on? Come back here. And let's try to apply what we just saw and see if we can figure out what's going on around this vertical asymptote. Now hold on, what number is this vertical asymptote? Where is he at? X can't equal who? Okay. So I need to come from below negative 2 and I need to come from above negative 2. Okay? You guys remember how we show that? As x approaches, how do I come from above? Negative 2 from above, a little plus. As x approaches, we'll fill it in a second. And this one, as x approaches negative 2, how do I show from below? A little minus. F of x approaches. Okay, and fill in the blanks. I know both of them have infinities. I need to check the, did you pick it up? Check the sign. But how? Choose two representative values that fit in the case of negative 2 but a little bit above and negative 2 but a little bit below. Trying to piecemeal it so I can actually get this. There we go. Okay. Have you guys been thinking about it? What's something I could plug in that would be negative 2 but a little bit above?
1.9.
Negative 1.9 or negative 1.5 or negative 1.2. I don't care. So let's take our 7 plus 2 times. Let's see if we can still do this. It's going to be a little bit harder on the brain. So let's do negative 1.9, negative 2, but a little bit above. Yeah. Kristen, what's your question?
Oh, I was just gonna ask why we couldn't do like negative 1 or something like that, just the closest to 2, you're saying, like 1.9.
We can do negative 1, but the problem is sometimes a function might start above and then go below. So when we zoom in really close, we're almost guaranteed that it's already headed either down or already headed up.
As close as,
Yeah. And we don't need to do the number, remember? We're just looking at the sign, so hopefully we can figure it out. Like, I know, it's a little bit hard. How do you multiply 2 times point, or 1.9? Approximate.
It's around negative 4.
It's, yeah, because that's 2-ish, right? What's 2-ish times 2-ish? 4-ish. Negative 4-ish plus 7 is definitely who? Positive. Positive. Definitely positive, right? All over, hey, what's 2 plus negative 1.9 or 2 plus negative 1.5 or 2 plus, is it a negative or a positive? All right, who wins?
Positive.
Positive infinity. That's where we're going. Don't you know? Okay, you guys, see if you can figure out. Remember, it could, from both sides, they could both be going to positive, both be going to negative, or going opposite. But right now, coming from above, I know somehow this function is going up. You guys, I want you just to try picking something on the other side of -2, plugging it in, and see if you can figure out what the sign would be. Remember, we don't get the number, so we just use a sign. And we want close to -2. East is saying -2.1, what do you guys think, is that on the other side? Sweet. You could do -3 in this one, but look at like -4, -5, as you get further away from -2, all bets are off, we need to get in close. Question, 2 times -2-ish. -4-ish. -4-ish plus 7 is for sure positive. Okay, he's, uh-oh. What's 2 plus -2.1? Or 2 plus -2.01? 2 plus -2.5? Who wins? If you were to graph him, guess what you would see? Something like that. Something like that. Now, the problem is, it's not perfectly like that. Let me show you actually what it would kind of look like. Because I could actually, with teaching you one more clue, I can go one better.
Teach him up.
And I can say, not only is it going up, which it is, and going down, which it is, but it's also
That's why you can't plug in
That's why I
-4.
can't plug it in. -4, -5, -6.
Yeah.
Now what on earth am I showing you? The down and the up comes from here, right?
Horizontal.
I'm showing you a horizontal asymptote at. But how did I know that? I found the ratio of the leading coefficients when the degrees were tied. But that is not enough for you guys to be like, psh, got that, give me a test on it today, so let's go talk about it. Horizontal asymptotes. Here they are. You've seen them before, but we need to review them just a little bit. Some of you are like, degree what? Ratio of the leading coefficient, what? He's like, no, literally, what? Horizontal asymptote. Hey, look, arrows all over the place. But we know what those arrows mean, and we know how to read them. Move it down just a little bit. A horizontal asymptote occurs when f of x, the y's, arrow approach. Huh. I'm going to fill in a couple of these blanks. We're not going to get as crazy hard as we do with horizontal asymptotes, and it's not crazy hard. We won't get as tricky as we do in calculus with them. So you kind of have to learn some calculus first. But we can do basic ones. And actually this whole idea of a degree test comes from calculus. It's just kind of trickled down as a shortcut for pre-cal kids and algebra 2 kids. Come on, it's a good symbolism. What's going on if x approaches negative infinity or positive infinity? Where are we headed in our graph? X, horizontals. If x goes to positive infinity, what's going on? We're going to the right. And if x goes to negative infinity, we're going to the left. So, quick reminders. Oh my goodness, you guys are crazy. It's the PJs. To the left. Maybe it's all natural. To the right. Okay, going to the left, going to the right. That's end behavior. Wait, that's leading coefficient test. Wait, we did that last chapter. Okay, sweet. So when we had an even degree, we talked about this today. When we had an even degree and a leading coefficient is positive, what's going on to the right, to the left? Oh, we're going up, which means f of x is approaching positive infinity. And if I don't know, the leading coefficient is negative and we have an even degree polynomial, we're going down, which means f of x is approaching negative infinity. Question, is there a horizontal asymptote of him? Why not? Does he have a horizontal asymptote?
Yeah, under the vertex. No, he doesn't.
He has a horizontal tangent line, that's calculus. Get back. Horizontal asymptote? No. Because what's going on as we go to the ends?
They just have vertical asymptote.
What's different in the graph you guys just saw that made it have a horizontal asymptote? Where was it not going?
Oh.
It wasn't going up, it wasn't going down, it was getting closer and closer to, like an L thing. It was getting, just stop, in the sense of, look at the graph. What was it getting closer and closer? Now, I know, it kind of was going down, and it was going up, but it wasn't going to negative infinity, and it wasn't going to positive infinity, it was going closer and closer to a, maybe an axis, but some sort of line, horizontal, some sort of constant, some sort of number, some sort of horizontal line. Getting closer and closer to some sort of horizontal line at. If y equals 0, it's the x-axis. If y equals 2, it's the line at a height of 2 like you just saw. How do we do horizontal asymptotes? Well, first of all, we tell ourselves or remind ourselves, you're only going to have horizontal asymptotes of rational functions, first of all. Basically, you're going to have a top that's trying to do his own thing and a bottom that restricts him. And if he restricts him strong enough, if the bottom is strong enough, it'll pull the heights towards and limit it by a horizontal line. Beware the denominators, in life and in math. But, coming back, if the bottom is strong enough, it's going to stop f of x from doing what it wants to do, and it's going to pull it down and restrict it and have it get closer and closer to a horizontal line. So how do we figure out whether the bottom is strong enough? Compare the degrees of the top and the bottom. And we're just dealing with ones that are going to have polynomials. In calculus, you get to ones that have like e's and ln's and square roots and all this jazz. We're just looking at degrees of polynomials. If the top wins, he can do what he wants. If the top wins, he can do what he wants. He's not restricted. If he's not restricted, there's going to be no horizontal asymptote. None. If the top wins, nothing's pulling him down, so he's going to be going to infinity or negative infinity or doing something or others, meaning the y values. If the bottom is stronger,
Y equals 0.
not only is he pulling them down, but he's pulling them all the way down in the sense of a horizontal asymptote at y equals 0. And then, if the degrees are tied, the degree of the top is equal to the degree of the bottom, as you guys just saw me do a second ago, then the horizontal asymptote is going to be at the ratio of the leading coefficients. Horizontal asymptote at the ratio of the leading. If I can spell coefficients. So when's the only time that there's a horizontal asymptote? Just those. The top wins, there ain't anybody pulling him down. And he's gonna go wherever he wants to go. Okay, so if I was to show you something like this one, what would you guys do? Look at the degrees. And if you want, I'll totally judge you if you actually even like let your eyes zero in on the degrees. The 5 doesn't win, the x squared wins, right? So the terms with the highest exponent, who wins, top or bottom?
There is none.
Top wins, no one's pulling them down, so what's that mean?
No. Horizontalized.
None. Right? But what if, I'll just show you that one. Who wins? Why? He has an x, he doesn't even have one, it's x to the 0. Bottom wins, uh-oh. He's pulling them down in a big way. Right? So as you go to the right, to the left, this thing's getting closer and closer to 0. Last one. He's the one we just saw a little while ago. Who wins? No, not the degree. Not the degree. Who wins the degree?
They're equal.
They tie. They both have x to the first power. They tie. But he's still pulling them down. So there's still going to be a horizontal asymptote, but a horizontal asymptote at 2/1. Hence why I said a second ago there was a horizontal asymptote at 2 and I changed my graph just a little bit. There was a tie. Okay? We talked about vertical asymptotes, behavior near them, horizontal asymptotes, behavior near them. I wonder if there's anything else that we need to talk about. Hold on.
Oh shit.
Oh my gosh.
Let's pause. Let's go to the slanty asymptote. Slanty one. Slanty one. See, I told you we were going to finish it today. Now, the snazzy name for a slanty asymptote is an oblique asymptote. Oblique. You guys can see it there, right? Oblique. On fleek. Just kidding. Weirdest saying ever. Okay, so slanty asymptotes. Then we'll talk about what's going on the next 2 pages. Slanty ones. Well, one's an example and one's stuff to actually talk about. There is going to be an oblique asymptote when the degree of the numerator is higher, and hold on, we gotta add something, is 1 higher. Is 1 higher. Literally, it's only allowed 1 power away. When the degree of the numerator is only 1 power higher than the degree of the denominator. Now, as a result, a slanty asymptote happens when there is no horizontal asymptote. Because the top is winning. If you look at this, the top wins. That bottom isn't pulling them down. But he's still pretty powerful. He's still having a big effect because he's only 1 degree away. If he was 2 or 3, he's gone. He's gone. But since, in this example, it's only 1 away, there actually is a slanted asymptote. And a slanted asymptote is going to be at y equals mx plus b, because a slant asymptote is a line. How do we find the slant asymptote? Long division. And long division says, okay, you know what to do, so do it. And we're like, all right. We won't kill any seals because we're better than that. There's a remainder? Yeah. But when we find a slant asymptote, we ignore the remainder. We ignore it altogether. And we just say, hey, there's going to be, we could call it an OA, an oblique asymptote, or we could call it a slant asymptote at y equals, and we just steal the answer. It's weird, crazy, and a little bit trippy, but believe it or not, if you were to go and graph this function, guess what my function is doing? he's limited, but he's still going to infinity and negative infinity. But he's limited by this slant asymptote. And kiddos, 2-6. 2-6. We have done everything, but look at how to put it all together. Hold on. Look at how to put it all together and say, hey, here's a nasty guy, let's figure out all this stuff and see if we can make a picture. Okay. So tomorrow at the beginning of class, we're gonna see if we can put it all together and make a picture. Here's the problem, we're going on to 2-7 tomorrow. Which means, what do you need to do tonight?
2-6.
Homework, everything but. If it says sketch, just skip. Sound good? Alright, bye guys, see you later.
I'm just next. You want to do that?
If it says like figure out all
Alright, I'll
these
see you
things
there.
and make a graph,
Pitch all picking it.
wait.
He's got a gauge.
Would you like us to do that?
Or but you want to do like the X guys that.
Yeah, because then you have really, you won't have to worry about the order. Does that make sense? Thank you, thank you. This is
Gonna miss me when I'm gone. He said you're gonna miss me when I'm gone. When I'm gone.
You're gonna
Show Eric, show Caleb. They're gonna get thicker. But for right now, they fit. Thank you. Two. Easy. Perfect.
Little baby BC.
Beautiful and organized.
Getting thicker.